Okay. Welcome to the afternoon lecture. My name is Renato Renner. I'm leading the Quantum Information Theory group at ETH Zürich. We are mainly doing quantum information theory, so I'm a pure theorist in that sense. And I'm also I have a lot of interest in quantum cryptography. However, I was asked to talk about, or we kind of agreed that I will cover different topics. And actually, Stefanie Wehner, who will arrive tonight and lecture tomorrow, will cover quantum cryptography, whereas I will talk about quantum thermodynamics. So maybe this is a topic that is actually, maybe a few years ago, people wouldn't even have said that this belongs to quantum information science. But the situation has changed a lot. Quantum thermodynamics is now kind of a very active research field where many people with an information theory, or in particular quantum information theory background, are working and trying to contribute and actually at least trying to get a different understanding of sometimes pretty old laws, like the second law of thermodynamics is now researched on from a kind of purely information theoretic perspective. Maybe I should in that context also mention that in Europe there is even now a network called the COST network on quantum thermodynamics, where many groups, actually I think more than 30 groups from Europe are kind of connected. They organize schools and conferences and so on. So if you are, maybe after this lecture, more interested in this topic, there are possibilities to enter more into it. And there are also many conferences and so on. So there is a platform in Europe that connects researchers with an interest in this area. So, and this platform is also open to researchers from kind of with different backgrounds. So there are, of course, the quantum information scientists, but there are also the traditional mathematical physicists who are working on these topics. There are also many experimental groups who do experiments connected to quantum thermodynamics and so on. So maybe we'll tell you more at the end of the 3 lectures that I'm giving. Then I can give you also more details on what is really going on and what the actual current research questions are. So maybe I should also encourage you to ask questions. Of course, I can easily talk for the 3 times 1.5 hours, but I think you learn much more if you interrupt me as much as possible and ask questions whenever something is unclear. So I think it's much better to cover a smaller kind of subset of material, but more thoroughly. And this is only possible if you tell me where you have problems in understanding and where you would like to hear more. So please feel free. You should even not feel free, you should feel forced to ask questions, maybe. So what I'm going to do in these hours is so today you will not hear the word quantum very often during my lecture, because when you start learning about thermodynamics or quantum thermodynamics, the first thing we need to do is to try to revisit certain concepts that may be familiar to you, like entropy and so on, but from a more information theoretic perspective than the usual treatment of thermodynamics. So the whole approach, this modern approach to quantum thermodynamics, is to a large extent based on information theoretic methods. And I would therefore like to tell you how information theorists see thermodynamics. And this, how this is done can be understood in a completely classical picture, or actually in a picture which I should say is just more general. It includes the classical description, but it will also include the quantum description. Then tomorrow we will be more specific and actually do quantum thermodynamics, and on Wednesday we'll continue that, and on Wednesday we'll also try to show you a little bit what type of open questions we have. These are sometimes very fundamental questions related to the basic laws of thermodynamics, but also experimental questions, and what approaches we follow to solve them. So I'm sure every one of you has heard thermodynamics, either in a basic physics course or even in a dedicated lecture to thermodynamics. And maybe you have noticed that traditionally thermodynamics is actually a very old science, and it deals with kind of macroscopic objects. So it has been invented even to analyze the efficiency, for example, of steam engines in the past, or fridges and so on. So these are all objects that are kind of, in our perception at least, fully described by classical physics. Now, what is going on now recently is that people realize that we can also manufacture very small machines. We can even control individual qubits. And we may now ask whether the thermodynamics that is applicable to the large systems, to steam engines and so on, carries over to these very small systems, whether the same laws still apply or whether we have to change them. Or maybe there's even something fundamentally wrong with the laws if you go to very small systems. That could also be. So the general question is kind of a fundamental one and a very practical one. So we just want to understand which laws, and maybe the whole of thermodynamics, is applicable if you go to nanoscale systems where quantum effects become relevant. So that's kind of the bigger question. So specifically, I mean, when you talk about the applications, there are two types of things that one would like to answer. So the first type of question is, if you think of a steam engine and you would ask the question, is it possible to make a very, very small steam engine? How small can you make it? Maybe you no longer are interested in the steam, but you want to have a heat engine. So you would like to have a machine that is kind of connected to two heat reservoirs and transforms the heat or the heat difference of these, or uses the heat difference between the two reservoirs to extract usable work. That's what a steam engine, for example, does. That's also what a car engine does. But you could now ask, what is the smallest machine that achieves this task? And maybe it's possible to do that with something that is only, I mean, if I talk about small, we could talk about the size of a Hilbert space in the quantum domain. Maybe this is possible with just a quantum system that is very low dimensional, maybe just lower than 10 dimensions or so. And actually the answer will be that this is possible. So we can understand a heat engine in terms of qubits, so it will be a machine or a device that just consists essentially of 3 qubits. One will be connected to a heat reservoir that is hot, the other one to a cold one, and the third one to a kind of work reservoir. And if we couple these 3 qubits in a clever way with each other, they will exactly do what a heat engine usually does. You could also run it in reverse and use it as a fridge, so it would use work to create the heat difference. So that's one thing, and this is of course connected directly to experiments. So one can now today manufacture qubits and the necessary the required interaction in such a way that you can do all that. At least that's possible in principle. In practice, there are several problems with robustness and so on, and we will talk about that a little bit later. The other kind of application is if you think in the other way around. So we already have qubits and so on, and we would like to use them to build a quantum computer. But you know that any computer, when you run it, dissipates heat. And actually the heat dissipation of a computer is one of the main limiting factors in making the performance better and increasing the computing power. So when you build a supercomputing center today, then the main consideration is you have to cool the machines. So you have to build the supercomputing center ideally next to, for example, a river where you can use the river to cool things. So this is really the limiting factor. It's not. So when you want to know how many operations can you possibly do per second, then you just have to calculate the amount of energy you need per elementary calculation or per elementary gate. And this energy will, of course, be dissipated as heat. So if you kind of get as a result that you create an enormous amount of heat, you just have to think about how do you get rid of this heat. Or alternatively, you can ask the question, can I make the elementary operations more efficient? Is it possible to build the gates, the individual computing steps, in such a way that they only require a minimal amount of energy and therefore only dissipate a very small amount of heat? And quantum thermodynamics will give us fundamental bounds, or at least the methods to calculate fundamental bounds on how much energy we need for computations. So these are the type of applications I have in mind. Okay, so this was kind of an introduction. And so I will now start, as I said, with the information theoretic approach to thermodynamics. So I will tell you to what extent we can use information theoretic methods to understand thermodynamical systems. And in order to do that, I would like to start making, or maybe explaining a distinction that I will make during all the lectures between what I call phenomenological thermodynamics and statistical mechanics. Because when you learn thermodynamics, you often learn both of these things. And if you're now kind of making things precise, it's always good to be aware of where we are. Are we now talking about the phenomenological approach, or are we talking about the statistical mechanics approach? And of course, there are as many definitions of that as there are physicists, but so the actual distinction is maybe not, so the actual definition is not so important, but maybe the approaches that are behind it, or the main ideas, they're kind of different. So one thing which I call phenomenological thermodynamics is kind of based on the idea that we can actually make statements about the thermodynamic system without understanding the microscopic mechanism that is underlying the, that governs the physics of the system. So the defining feature is that it's kind of only based on measurable quantities, on experimentally measurable quantities. So this is now a slightly vague thing, if I say experimentally measurable quantities, because you could say that in principle I could measure everything. But this will exactly be the point. So the framework will kind of be based on a set of observations that we consider as feasible. And depending on what is feasible, we will get different conclusions in our statements, which is fine, as we will see. But the other thing is that it's independent of a microscopic model. And if I say here microscopic, maybe one should say these experimentally measurable quantities are sometimes called the macroscopic one. But this term is now, as we go to quantum thermodynamics, no longer so appropriate, because even microscopic things like the spin of an individual particle may be measurable, and then we have to treat it as a macroscopic quantity, as we will see later. So here I should say the model doesn't even need to exist. The model does. And what I mean by that is that, I mean, you can maybe easily imagine that thermodynamics, as I said, was used to understand steam engines and so on. This was at the time, like more than 200 years ago, where people didn't even know that a gas consists of particles. Nevertheless, they could make sensible statements about the behavior of the machines. And this is exactly because the theory, this phenomenological theory, does not depend on anything about the microscopic things. So the theory would also work if actually microscopically there would be a fluidum which cannot be kind of decomposed into individual particles. There would be nothing wrong with the theory on this level. Then the other thing is statistical mechanics. And here one considers a model, or it is based on a model a microscopic model. So the idea is that one starts with something that really describes everything of the system, like each individual particle, and then one introduces methods to deal with situations where most of the degrees of freedom of the system are unknown. So that's what we do in statistical mechanics. In statistical mechanics, for example, we describe a gas as, I mean, even classically, as a set of particles with individual positions and momenta. And then we use probability theory in order to capture a situation where we don't know the individual positions and momenta of the particles and only know certain things about, for example, averages and so on, or boundary conditions. So this is what is done. So it's a very different approach. You see, this is kind of a bottom-up and starts really with the details and then builds up a framework which allows us to make statements about maybe macroscopic things like pressure and temperature. And here we start just with the experimentally measurable quantities like pressure and temperature, and then never needs this microscopic model in order to make statements. So this is the distinction I would like to make. And I would now like to start giving you, because I would like to explain a few things within this framework of phenomenological thermodynamics, and because this is taught in many different ways, I would like to spend maybe 20 minutes introducing some formalism and revisit this framework of phenomenological thermodynamics. So what you will now hear in the next 20 minutes will be mostly things that you probably have learned in one way or the other in a thermodynamics course. But the important thing is that I will need certain formalism and also certain aspects that are maybe done sometimes in a different way. So I have to define it here again. But I hope it will, even for those who know it, not be too boring. And otherwise, let me know if everything is completely well known. But let me, in order to tell you what I'm aiming at, let me first just make a little sketch. So let's assume we have something like a steam engine. So this is something we can all imagine what it is. And then there are certain what I called experimentally measurable quantities, or what would traditionally in standard thermodynamics be macroscopic quantities. For example, this thing has a temperature, T. And it also has, for example, an entropy, S. And actually, because entropy, such as energy, can be defined, or is always defined with respect to a reference, the actually relevant thing is usually an entropy change. So I will call it that ds. So we talk about entropy changes. And a steam engine will, for example, consume certain heat. This is usually called delta Q, the heat, and it may produce certain work. So this is, the work is kind of the rotating wheel or so, and the heat is coming from the steam and so on. And maybe it will also give up some other heat into another reservoir. So this is some d delta Q prime. This will be kind of the cooling of the steam engine. So we have different quantities. And now what is important in the information theoretic approach that we are taking is that in information theory we are very much used to the fact that information or any quantification of information is kind of observer dependent. So this is very natural. If I, for example, ask you what is the entropy, you have probably already heard about entropy. What is the entropy in the traditional sense of a coin that I toss? So if I toss a coin, this is not a coin, but if I toss a coin and I ask you, what is the entropy or uncertainty you have about the outcome of this coin toss? Then probably most of you would say it's, those who have at least heard about the notion of entropy would say it's 1, because it's 1 bit that I would need to tell you, heads or tails, so that you know that. So from your perspective, the entropy of the coin toss is 1. But if I have looked at the coin, then for me, the position of the coin has no uncertainty because I already know it. So for me, the entropy of the coin, at the same time, while it's 1 for you, is 0 for me. So the notion of entropy in information theory, at least, this is now not the notion of entropy in thermodynamics, is an observer-dependent notion. It depends on who talks about the system. So the entropy is not a property of the system, or of the coin in this case. It's a property of my knowledge about the coin. And one can now ask the same question here. So here we have something like at least some quantity that is also called entropy. Maybe it's something different because it's a different framework. But we may now ask, and we have to ask this question in the information theoretic approach, is this a property of the steam engine itself, or is this just a property of our knowledge about the steam engine? So who thinks that this is kind of an objective thing? so by objective, I would mean that every physicist who would analyze the steam engine would assign the same entropy to the steam engine, or the same entropy change to a certain process. So who thinks it's objective in that sense? Okay, yeah, so many. Who thinks it's subjective, so it depends on the observer? Okay, so it looks like 50-50, so we don't know. So it's either subjective. I will tell you the answer later, but we don't know. Yeah. So what about the temperature? This is easier. So who thinks that every physicist would analyze the same steam engine and, for example, measure the temperature of the gas, and let's assume it's constant, so I'm not talking about fluctuations, would assign the same temperature? Who thinks this is the case and it's therefore objective? Yes. And who thinks it's not subjective? Okay, no. So this is seen as objective, and I would also agree with that. So temperature is something that, I mean, we can measure with a thermometer, and everyone would agree that it's the same temperature. What about the heat? I mean, this is, for example, the heat flow. So, of course, there's heat flowing in the gas. So who would think that this is an objective thing? Who would think it's subjective and depends on an observer? No one? One person. Okay. So it seems that we said here objective. Now, actually, we can already derive here something about that, because maybe you have seen this formula, ds is equal to delta q over t. So if we all agree that this is objective and this is objective, then what can we say about this? I mean, this is a definition. Then this has to be objective as well. So what you essentially said, if I now take the majority vote, is that this is objective. Okay, but here you said you're not sure. So who would now still think that this is just subjective, the entropy, after this little argument? You think it's still subjective. But what would then be wrong with this argument here?
Well,
maybe you were the one who said.
Yeah, I guess I was. But I think that if you look at every single atom in this, I mean, I say that it depends on the model. I mean, if you calculate the movement of every single atom that collides when gases of different temperatures mix, then you would get another uncertainty than if you just have just this statistical approach.
Yes. Okay, I mean, it's right. So what you will see, and this will actually be the main point of today's lecture, is that this is wrong. So this is indeed, I mean, as you said, this is subjective. So what the entropy is that we assign to a system is clearly depending on the observer. Different observers, and I will give you a very convincing example later. Maybe this is not so clear at this point, but depending on two different observers with different points of view, will assign completely different values to an entropy change of the same process. But this means now, in order to be consistent, that at least one of these two quantities has to be subjective as well. And we will see that also this answer here was wrong. This is actually a subjective thing. So the heat flow we have in a system is a completely subjective quantity. So the only reason why this is against our intuition, because of course the intuition that most people have is indeed that this is something objective. So the reason for this intuition is that usually the systems are very large. And if the system is large, then most reasonable observers will roughly have the same kind of view on what heat is. Once we go to small systems, it will be pretty obvious that this quantity will depend completely on the observer. So this observer dependence that I'm claiming that this quantity has just disappears in a kind of macroscopic limit, seemingly. It's still there, but it kind of seems to disappear, and that's why one usually thinks it's objective. So that will be essentially the motivation of today's lecture. Yes?
What could be, for example, two different observers be in a quantum mechanical system? So I'm asking, what is an observer actually?
Okay, so this is a very good question. What does it mean? And if you allow me, let me continue because this is actually the main, let's say, content of the lecture. So this is what we will learn. So I will actually answer your question now. It will just take an hour, which is the lecture. So this is exactly now the question we would like to consider. What does this mean, all that? Now I was very vague. I said, okay, this is now subjective, and maybe this sounds very vague and not well defined. Now the purpose of the next hour is to make all these things much more precise. And that's why I said, I need to revisit the standard framework of thermodynamics. So even if you have already learned thermodynamics, probably no one told you so far that there is a kind of a problem if you don't consider the heat as a subjective quantity. So that's why even if you have already heard thermodynamics, you should probably listen, at least if you were among the ones who said that heat is objective. Okay, so I will now, this was just to kind of give a short outlook of what I'm aiming at in this kind of review of thermodynamics. Maybe I should clean that a bit better. So, okay. So what I'm now, as I said, going to is kind of a short review, and it's kind of a more formal review than usual of phenomenological thermodynamics. And the nice thing about this theory, I mean, phenomenological sounds like something very kind of unprecise. But the nice thing is that phenomenological thermodynamics can be built on a very well-defined and mathematically very clean framework. So there is a mathematically very satisfying way one can talk about phenomenological thermodynamics. So phenomenological doesn't mean that one is actually not precise. It just means that one doesn't rely on an underlying microscopic model. So the framework one uses usually is the following. And by the way, what I'm now telling you is largely motivated by a paper which is very nice by Lieb and Ingvason. These are mathematical physicists who try to really understand what thermodynamics is on a fundamental level. And of course, I mean, they make the treatment much more mathematically rigorous than I'm going to do that now. But I will give you kind of the main idea of what they're trying to do. So the framework is the following. So one says that a thermodynamic system, and by a thermodynamic system you should imagine, again, for example, a steam engine or a fridge, is essentially described by a set S of states, or actually this state is usually, use this notation they use, they call it usually sigma, but we will not use that, of states, and a set A of what is called allowed adiabatic processes. And so each such process will have the name pi. So I will call these adiabatic processes pi. I will just tell you what they are, but let me first say what mathematically what properties have. So any such process pi of this corresponds to a state transformation. So what a process does is it transforms the state of a system. So Z is an element of this sigma to another set, which I call Z prime. And this is also an element of sigma, and this is why the process pi. And any pi has a work cost. Maybe I should call the thermodynamic system just because later I will have more systems. Let's call it S. Any pi has a work cost, which I call WS for the system of the pi. And this is just a real number. So now I should maybe make an example. But, okay, so if, I mean, a thermodynamic system, a very simple one, which I will often consider as example, is just a piston filled with gas, or a cylinder filled with gas and a piston. So this is the system S, or would be kind of something filled with gas. Of course, it's, as I said, irrelevant whether these are now particles or not, or just some fluid. So this is just to illustrate it. And this piston, so now a possible state of the system is this one. And in this particular case of a piston, the state could be characterized, for example, by the volume of the thing, or the pressure, and the number of particles. And then another state could be, for example, one where I've expanded the cylinder. So this would be another state, Z prime, which has some V prime, P prime, and maybe the particle number stayed the same. And the process will be, for example, the transformation from here to here. That may be pi. And of course, I could now, in this particular case, calculate the work. And the work would kind of, in that case, be, I mean, you know that for a piston, this is well known. It's just the volume change times the pressure integrated from V to V prime. Now, what this framework does, it kind of starts from the opposite way. I mean, you could now ask yourself, what are the states? So the framework just says, this is what you have to define. So you just, for a thermodynamic system that you take, you first define a set, which you define to be the set of states. This is kind of something you have to impose on the system. This is not given. And of course, what this set of states is depends on the system. If I look at a more complicated system, then I have a larger set of states. And then you have to ask yourself, which processes are possible? And so it says adiabatic. So what this, a priori, you can just define any set of transformations. But of course, in order to capture a particular physical system, you should ask yourself which processes are actually feasible, and adiabatic just means without the help of bringing the system into contact with anything else. So you just have only the system, and you have certain handles to the system, like this piston that you can move, but you cannot do anything else. You can, for example, not put that system into a fridge and cool it down. This is not allowed. I mean, that's kind of by definition, but essentially mathematically you specify by this set what you define to be allowed. So you could say that if you see a system, you ask yourself what are its states, you define that as the set sigma, and you ask yourself which are the processes which you can carry out, and you define this as the set A. And so that's from what we start off with. And of course, you can do that for any system, and depends, of course, in general, of your experimental ability, which processes you consider as feasible. But in principle, any set of such processes can just be defined as the necessary set.
Can you say something about the word adiabatic in this context?
Yes.
What is that supposed to mean here?
Yeah, so my point was kind of this is really defined by the set. So in some way you could say, I mean, physically what it's supposed to mean is that the system is not, so these are processes you can carry out without bringing the system into contact with something else. But this is, of course, just words. What does it mean to be in contact with something else and so on? So the idea of the framework is really this is kind of just given a priori. So you define the set and define this to be the set of adiabatic processes. It's kind of the opposite way. So it's not that there is already a notion of adiabatic process. You kind of give the set, and then by definition, any process in this set is adiabatic or not. Now, of course, later we will kind of impose certain constraints. And the constraints will be the laws of thermodynamics. And if this set is too large, so if we include stuff that is actually not possible physically, then we will see that we will run into a contradiction with these laws. But a priori, up to this point, you can just define any set you like as a set of adiabatic processes. It may then just be that you will violate the second laws, and then you would say this is then not a valid kind of theory of thermodynamics. But so at this point, there is no definition of adiabatic. It's just defined to be all processes in that set. Okay. Now, but when you apply the framework to an experiment, you, of course, would like to ask whether these are possible things. So now, one additional important notion that we need to introduce is that you can usually, when you have two systems, you can kind of also look at the joint state space. So the other thing is that in this framework is that systems can be composed. That's also very natural. Of course, I mean, composed just means instead of looking at one system, I look at two systems. And then the state space, so I get a new state space, or let's say I have some system 1 and some system 2, and this has a state space sigma 1 and sigma 2, then there's a joint state space. And I could sigma 1, 2, and this state space at least has all the product states. So, of course, any state that this system can have and any of this one gives a state of the total system, but I also allow that the joint system, if I have both systems, can have states which cannot be written as a state of this system and this system. This will, of course, be important in the, for example, in quantum mechanics, because as you have learned this morning, if you have an entangled state, it would be not representable in this framework if I would require that the joint state space is just a set of product states, of course. But even in classical probability theory, this would actually be a problem. So I'm just saying that if we have two systems, we can compose them, and then there is an operation that defines us what is the larger state space. And the same with the operations. So there's a joint space of the adiabatic processes, 1, 2, which is also at least contains the adiabatic processes on the individual systems, but you may, of course, do joint things, like you can somehow do something which involves generically both systems. And in this case, you have an operation that you cannot write as an operation on 1 and as an operation on 2. So this is essentially what we need to formulate things. Now the last thing we need to define this framework is now I have introduced this notion of adiabatic processes as a basic set. Now when you can compose systems, you can do more general processes. So a general process is defined as the following. I call that usually tau. A general process takes a system, let's say system S, and now we compose it with some additional system, A. So this is, we just take an additional system into our consideration. Then we do a joint process pi AS, or SA. This gives us, again, I mean, this is a process on the joint system, so we still have both systems. And now, finally, we just restrict our attention. Maybe I should make that a little bit larger. We restrict our attention again to the system S. So this is kind of a very simple thing. This essentially expresses the fact that, in general, I'm of course not restricted to act on a system alone. I can always put the system next to another one and then do something jointly on the two, and then at the end, again, just focus my attention on the system S. And now, if this system was in a certain state set, this will be in a certain state set prime. And even if there, I mean, it could be that there is no process, no adiabatic process that brings set to set prime. So it could be, so this is a note, there may be no pi in this set of adiabatic processes for the system S, such that set is transformed to set prime with pi. but there could still be a general transformation as this way, a general process tau. So what this tells me is a very simple thing. It just tells me for certain transformations I need to bring the system into contact with another. So let me again make an example for that. An example is actually almost the most trivial example one could think of, is just cooling down a system. So I don't even need a piston or so. I just need essentially, let's say, a vessel filled with gas. So the specific example could be, I have here a gas thing, and this has a certain temperature T. I mean, I haven't defined temperature formally yet, but we can already, as an example, for the purpose of the example, think of this. This would be T prime smaller than T. So if you don't bring the system into contact with anything else, there will usually, I mean, this is now a matter, of course, of definition at the end, but if you define the adiabatic process really as the things you can do in the lab without bringing the system into contact with anything else, there is no way you can cool down a system. If it's completely isolated, it will always stay hot. So there is no process from here to here. But of course, what you can do is you can here bring the system into contact with something cold, a cold reservoir, and then just wait, and then the system will, of course, cool down. So there is a process that cools down the system, but the point is you need to bring in an additional system in order to do that.
You frequently just repeating the adiabaticity in the system, the adiabatic that you have.
Yes.
So does this mean I don't have none of them when I'm just dealing with non-adiabatic system or something like that? Can I have the same physics in the case of non-adiabatic system?
So one really starts this framework by just defining what is an adiabatic system. And this is now essentially a non-adiabatic process. That's what it means. So a priori, so one should maybe think of it like that. If you define, for example, operations on a quantum system, you could first say, let's consider all unitary operations. This would kind of some way be analogous to defining the adiabatic processes. And then we can later say, actually a quantum system could be part of a larger system. And then on the larger system, we have an adiabatic or a unitary transformation. And if we restrict our attention to one subsystem, then we get a general completely positive map. So we get something larger than we originally considered. So in the same sense, one could say the adiabatic processes are like the unitary. They're those we consider on the total thing. But if we consider, this would still be an adiabatic one here from here to here. This is a pi. If we restrict our attention to an individual system, this gives a larger set of things, and these are the non-adiabatic ones. So I'm not really talking about adiabatic and non-adiabatic systems, but about adiabatic and non-adiabatic processes. And so I start with the adiabatic ones and then say that a subpart of a system, the evolution of a subpart is then kind of not necessarily an adiabatic evolution, and this is considered the general evolution. Does this answer your question? Okay, so this is all we now need. And as I said, and also to the answer, as an answer to David's question, we have essentially not required anything. I said an adiabatic process is just one of this set. And this is, of course, physically kind of a statement that almost has no content. And now to fill this framework with content, one introduces the laws of thermodynamics. So the laws of thermodynamics will essentially tell us that the sets that I introduced, the set of states and the set of adiabatic processes, have to fulfill certain constraints. And at the end, once you fulfill the constraints, it's irrelevant what you consider as adiabatic processes. As long as you fulfill the constraints, you have a consistent theory of thermodynamics, and you can do everything that one usually does in thermodynamics. Of course, the idea is that if you now define what we usually think intuitively as adiabatic processes, we'll just get our standard statements in thermodynamics. But the framework also shows that there's nothing additionally needed. So the only thing we need to know about adiabatic processes is that they're defined in such a way that they fulfill the laws of thermodynamics. And so there's no reason to talk about a priori about things like bring the system into contact with another and so on, because this would all not be very well defined in some way, unless I have a microscopic model. But the whole point of this theory is to work without a microscopic model. So there's one last thing I want to say, just as a kind of to have some terminology. So a process pi is called reversible. It's pretty intuitive. If there exists a process pi minus 1, I call it just like that, such that that pi minus 1 brings the system state back to Z. So the idea was, if of course I forgot to write that. So if I have a process pi which brings Z to Z prime, then it's called reversible. If there is also an adiabatic process which brings Z prime again back to Z. And the same for general processes. So a general, but here the definition is a little bit different. So general process tau is reversible if the underlying joint process. So you remember a general process tau was essentially composing a system and then carrying out a process on the system together with an additional system, an ancilla system. And if this joint process is reversible, then we call the process itself reversible. So essentially a reversible process is just one which I can see as a reversible process on a larger system. Okay, so this is just some terminology. And now we have all we need in this framework to state the laws of thermodynamics. And this is now the nice thing. So in this, the laws of thermodynamics are now well-defined laws. They just refer to objects in this framework. They don't refer to any intuitive things like as in the usual formulation, because that was often a trouble in the past, that the second law referred to notions like nothing changes except for this and so on. And of course, this is an intuitively well or sensible statement, but it's not completely clear what is meant with nothing changes and so on. And so the advantage of this framework is that this can be made precise now. So the laws of thermodynamics, they now make things precise. But let's first start, the first law is kind of the usually less interesting one, but it's very important to kind of make the theory consistent. And the first law consists actually of two parts. So let Z and Z prime be two states. So just two states of a system. Maybe call that, put here a subscript to say what system we are talking about. And now the statement, the first part of the law says that there exists a process, an adiabatic process, for which brings Z to Z prime, or a process which brings Z prime to Z. So this is maybe a somewhat surprising thing, but the first law, maybe you haven't seen this part, just says that everything is connected in the sense that we can either go so if you have two states, we can either transform Z to Z prime, or we can transform Z prime to Z. But anything can be transformed into another state. So what does that mean? Again, in this example of heating a system. So heating a system would typically be an adiabatic process, because I can heat the system without bringing it into contact with anything else. I just apply friction, for example. So heating a system. So if I have, again, this piston, but of course that is now, again, making connections to, let's say, a specific example. But let's assume, again, we have this example of a piston. Now what I could do is, for example, just move that piston in and out with fast. And this will, of course, I mean, this will heat up the system. So I can, by just moving here, this piston, I can essentially transform this T into some T prime, which is strictly larger than T. But there is no movement I can do on the piston to cool it down, as I said before. That's usually not possible. But so if I have now two states of the system, one which is colder and one which is warmer, there is a process that goes from here to here. So that's an assumption that I put in. So if you now would say, oh, this is not possible, then you don't have a theory of so you can essentially go to a lab and ask yourself, what are the allowed processes? And if there's no process that connects Z and Z prime, then you cannot build up a consistent theory of thermodynamics for this system. So you have to find such a process. And the law kind of says that this should exist. So if you believe in the first law, it would kind of tell you this exists. And the second part of the law is that so for any such processes, and this is the more well-known part, that brings Z to Z prime. We have that the work that is required for that is equal. So any two processes that do the same state transformation, any two adiabatic processes that do the same state transformation require the same amount of work. That's necessary, and that's kind of what the first law says. So the first law is sometimes also called energy conservation. And you see this is kind of something very similar to energy conservation. It says, well, however we go from one thing to the other, we will use the same amount of work. But note that a priori work was just some function. I just said the work we need to get from here to here is just a function of the transformation. Now the first law tells us, oh, but this function needs to satisfy certain constraints in order to be physically relevant in some way. Okay, are there questions so far? So this is just the first law. They will use that. Yes?
For part A, it said pi going from Z to Z prime and from Z prime to Z. Is that also the same?
Yes. So you need either. So if you have two states, you need either to be able to do that with some pi or with that. I mean, you could also have, because it's an or, I could equivalently have written, maybe it's more clear if I write it like that, but it's equivalent logically. I could have written, there exists a pi such that this holds, or there exists a pi such that this holds. So I'm just saying one of the two processes are possible. Yes? Yes?
So in the former case, we needed an auxiliary system to cool down the
yes. Yes.
gas parts.
Right.
So we have two disjunct areas in our state space.
Ah, no, because to heat it up, you can heat it up without bringing it into contact with another one. So indeed, what I said is we cannot, so there is, so if this is the hotter one, we cannot go from here to here. So there's no pi which brings us from here to here, because we would need to bring it into contact. But what the first law actually requires is, but because this doesn't exist, there must be some process pi which brings me from here to here. So this is essentially a requirement. So this is a good point that you're making. So the first law essentially tells us we have to have all states in our thermodynamic state space have to be connected. If this is not the case, you would just need to kind of consider these as two different systems.
So then we just need a different parameterization of our state space.
Yes, then your state space is somehow has too many elements or so. Yes. Or maybe your set of transformations has too few elements. So if you don't find the operation, I mean, this is actually something that will become very important because, for example, when you consider a gas with a certain number of particles, and you say that the number of particles that you have in the gas is part of the state, that you could define. I mean, I did that before in my example. I said n is the number of mole of gas molecules, for example, and this is part of the state. And if I'm now saying my state space includes small numbers and large numbers, then I need to have a process which allows me to actually add gas particles to the thing. And if I don't have this process, then this will not give me a consistent thermodynamic theory. And this is exactly the problem in some of the so-called paradoxes, that if one has different numbers of particles and, for example, compares the entropy of the systems, then one will get inconclusive results if there is no process that connects them. And the same is, for example, true for chemical reactions. So if you have two different, let's say you have a mixture between oxygen and carbon, or oxygen and hydrogen, pure oxygen and pure hydrogen, and you look at the reaction between the two, then this so if your state space includes the fact that you have also water, H2O molecules in this thing, then you need also to consider the process that actually includes the reaction, the chemical reaction that makes this. And if you don't include that, then there will be no way to connect the entropy of one system, or to compare the entropy of the individual pure components with the entropy of the water molecules. And this is fine as long as you don't want to compare this entropy, but if you consider that as a bigger state space, you need to include that. And so, for example, this will lead to the chemical potential. So what I'm saying is essentially the chemical potential, for example, would not be well defined if you didn't have this reaction. So this is actually really something that is often forgotten, but if you don't have it, you will run into paradoxes. We will see that later. Yes?
Do we need the same law for pi? I mean, like that for any pi there exist points z and z prime that such that pi connects them?
Aha, yeah, so maybe I wasn't, thanks for asking this question, but maybe I wasn't so clear. So the pi defines a state transformation. So yes, so this is already in the framework. So any pi so for any pi, I have a transformation from z to z prime, and I have a work cost w. So this is kind of, the answer is yes, but it's already included in kind of the definition of so when I wrote before that for any pi, there is a state transformation, this was kind of this law. Yes. This doesn't appear as an explicit law. This is kind of already built into the framework. By the way, this is always a question, what is already built into a framework and what are laws? But now I'm just following the standard way and define the laws as those that are usually considered as the laws of thermodynamics. And the fact that any transformation actually is a transformation of a state into another is just seen as part of the basic framework. Yes?
So just coming back to this piece, so we said that there is no closest time if you go from this higher
to the lower one.
We come to the situation where it's the gas performs the work, then you feel like
you say if I would use the gas to perform work in order to get from here to here. Yeah. Yes, I mean, actually, so far there would be no problem if I also allowed this process. But when we actually come to the second law of thermodynamics, we will see that this will then cause problems. And indeed, the process you suggest, so you're saying, I could actually let the thing expand, and then, of course, it will get colder, but then it will have a larger volume. And then if then there's no way I can again compress it without bringing it into contact with something else. So in practice, it will not exist, and indeed, formally, we will see that if it existed, it will violate the second law. But the first law doesn't tell us that also both operations are possible. The second law will tell us that in most cases, only one of them is possible. Okay. Now, what does the first law allow us to do? The first law already allows us to introduce certain quantities that you usually consider in thermodynamics, for example, the inner energy. And this is actually something I should just briefly mention, because that's probably completely clear, but let me nevertheless introduce it. So we can now define the energy. So this is now a definition. The internal energy of a system set, of a certain state, is defined as the energy of some, so this is just some reference state, which is arbitrarily chosen. And this is some reference value. This is also arbitrary. And this just expresses that kind of the energy is only well defined up to some additive constant. And then one adds essentially the energy, the work that is required to go for a process pi, and pi is a process from z to z, from z0 to z. So essentially, what I'm saying is that the internal energy is just defined as some arbitrary value of some state, and then the transformation from z0 to z. And if this is not defined, so then one just defines it in the opposite way. Because we know there's only one of the state transformations possible. So if only the one exists which goes from z to z0, that's also fine. Then I just need to put the minus sign here. But you see, the first law now tells us that I can for any state set, I can either write this or that. So it's always well defined. By the way, it's not, that wouldn't say it's well defined. I also need the second part, because if the second part wasn't true, then this definition would depend on the choice of this pi. So it would not be well defined. It could have different values. But the part B ensures that this is always the same value independently of which actual pi I chose here. So this is kind of, you see, the first law is needed to have a consistent definition of energy. And I think this nicely illustrates the whole idea of the approach. So we never needed to kind of say, the internal energy is kind of the motion of the particles in the gas. And you remember, I told you at the beginning, phenomenological thermodynamics is thermodynamics which doesn't rely on the microscopic model. People didn't even know that it exists, so they could never, 200 years ago, have calculated this U based on a microscopic model. But the first law allows you to calculate U just from quantities that are defined in this framework, which is just the work requirement of a process, which is something you can observe just from the macroscopic observables, for example, based on the volume change of a piston and so on. So in other words, this quantity is now well defined without that you ever have to know anything about the microscopic details. And this is only possible because of the first law. So the first law is in that sense much more than just saying there is energy conservation. The first law is really the necessary requirement in order to come up with a consistent definition of inner energy if you don't have access to the microscopic model of a system. This is what the first law does. Okay, so now as we have the first law, we can actually define heat. And now you will, this now looks kind of, will be important because I told you that the heat is a subjective quantity, but this will maybe from this point of view not yet be obvious. So I will just define, so this means the heat change. So I just look at an infinitesimal change from a state Z to a very close state, and then I have, of course, a change of the inner energy. So this is defined by essentially U of Z plus some delta Z, so this is some new state, minus U of Z. Or maybe I should write it like that. This is some Z prime, and Z prime is very close to Z. So that's just minus. And now I subtract the work. So what do I mean by the work? So this is now for so this is for a general process. And where this is defined as the work of the underlying process pi SA. So remember again, this now if I look at the general process, so maybe I should again draw this picture. I'm sorry, this blackboard is a little bit small, so I need to redraw a few things, but I think this doesn't hurt. So there's a system, and now a general process is of this type, that I have the system together with some ancillary system, and then I put here a joint process, and this joint process has some work. And then I again look at only the system S. So the heat dissipation of the system in this transformation from here to here, so this would be in a state Z and in a state Z prime, which is close to Z, is defined as the change of the inner energy from here to here minus the work that I needed in order to go from there to there. So this is now something that depends on the process. So it's actually maybe to be consistent. One doesn't usually do that, but it's useful to say here which process tau that I needed. So the process tau is the process from here to here, which includes putting the system in contact with something else and so on. So this is the definition of heat. Yes?
Can you define the equal sign? Like, it should not be continuous, right? In principle, your state set.
Aha. Yes. So. Yes. So this is a good. So now at this point, I jumped over a few mathematical things one would need to say. So the state space, in order to make this definition with infinitesimal things, the state space would need to be equipped with a topology so that I have a continuum of states. So if I had a set of states which would just be individual states which are far away from each other, then I couldn't write this. So in this framework, one needs to also say, actually the state space is continuous in the sense that it's a topological space. But yes, I jumped now over this thing. But I think it's probably okay for the moment for this overview. There are a few other things one needs to make a little bit more precise. For example, I need to actually say what exactly this delta means and so on. But I hope it's more or less clear, intuitive. Yes? Aha. Yes, one could in principle do that. The problem is, yes, so one can in principle do that. It's just that this is kind of a weaker definition in the sense that I only need it for close points. So the point is that, I mean, what you're saying is absolutely right. One could define it. It's just not needed in the framework. And so this, now one could say, okay, why don't I do things even if it's not needed? The point is I want to kind of stay reasonably close to the standard way thermodynamics is taught, and there one only looks at these processes. But you're absolutely right. In principle, one could here be more general. But yes. Okay. Now we are ready to actually formulate the second law of thermodynamics. And the second law of thermodynamics now takes a very simple form. So the second law says that if you have, so for any system, S and extra system C, so this is so essentially these are just two systems, but I'm kind of the additional one looks at the S. So this is the system S, and the other system is C, and I draw it around because I want that this is cyclic. So cyclic will just mean that I want to return this system in the same state as before. And if I now look at a process from here to here, so I have any arbitrary process tau. This is still the system S, and let's say the state of the system here is some state Z, and here it's some state Z prime. And the cyclic thing here is system C, and this is in some state, let's say, C bar, and C. This has to stay in the same state, so that's why, I mean, this is kind of a convention one draws this as round systems, because cyclic would mean that in a process they are returned in the same state. So I look at the total transformation between here, and now I can, of course, calculate the heat of this transformation of the whole thing. So now I'm saying that delta Q, and by the way, the convention is kind of that heat is positive if it's flowing into the system. This follows from the fact that the internal energy is the energy of the system. So if the internal energy increases, then also this quantity is positive. So delta Q positive means heat flows into the system. And what what the second law now says is that in this process heat flow. Oh, now I have to see whether I made this convention correctly, because yeah, maybe I should draw like that. So that the heat that in general I can only heat up the system, essentially. So this is what the second law says. So whenever I have a situation like that, then the processes tau are such that heat will flow into the system. There's no other way I can do that in some without. Sorry, I should say. Now I made a mistake. This should actually be an adiabatic thing. So this should be a pi. So this is something of this thing. This is some pi. Okay. So the point is that I cannot. So it's a pi on S and C. So on, if I would only look at this as a process from on S, it's a general tau, but on the joint system, it's something like that. So in other words, what this is formalizing is just this general idea that I cannot. There's no process that will take heat out of a system without changing anything else. So this anything else now just means that the state of this system here is not changed at all. So that's what the second law tells us. So this is probably not so surprising, but you now see that what the second law does in this framework is just it constrains a lot the set of what you are allowed to call adiabatic processes. So I could now come back to the question that was posed here. So if I could a priori in the mathematical framework, of course, say, this operation is also allowed from here to here. But if I now make the calculation and look at what is delta Q, then I will see that, of course, I mean, that's pretty intuitive, from here to here, heat will flow out of the system. So it would contradict this thing. So this says that whenever this process is possible, then heat flows into the system. So in other words, the second law is another law that just on this level constrains the things that are allowed, the processes. And this is now already all. We don't need to go to the third law. So in other words, what we have now seen is essentially that what thermodynamics on this very abstract level is just saying we have a set of states, we have a set of things we call adiabatic processes, and if these two sets satisfy the two laws, the first law and the second law, then we can essentially do thermodynamics in the usual way where we can define the things and so on. So one could now, for example, go on and use these definitions to define temperature. That's one possibility. I think given the time I shouldn't do that now in this overview, but maybe you should just believe me that once I have that, one can now continue in the usual way thermodynamics is taught. But the point you should get from this is that really, when you look at that, I just had to start, and we will now return with examples onto that. What I had to start with or put into the framework is I had to decide which are the operations that are possible. And now to come back to the observer dependence. Of course, this whole framework and all statements I'm making are, of course, obviously now depending on the operations which are possible. And it may now be that for different observers, and this will then clarify the question what an observer is, different operations are possible. And let me illustrate that with the example of the so-called Gibbs paradox that you may also be already have heard. But let's analyze a system from two observers' perspective. And now I will kind of make a drastic difference between observers in the sense that there would just be observers who live in 2 centuries. So I will have here an observer 1, and I call this observer 1865. So he's 150 years old that he did this experiment. And here is another observer, which is today's observer, who does this. Now assume that these observers have exactly the identical systems. So we give to this observer the same system as to this one. But we will, the two observers will analyze the systems, both in a completely consistent way. That's important. None of them will make a mistake. So I'm not saying that one of them will be wrong, although this is an old guy and he has less knowledge in some way. But so here the old one will have less knowledge because he will do the analysis based on whatever he knows about the system at that time. Now, what I'm going to do in order to constrain this observer is to say, let's assume you have the following system. Actually, this observer doesn't see that, so let's define it here. So I have two vessels filled with a gas, or yes, let's say a gas, but it could take whatever you like. In this particle, I have a gas with molecules that I put as crosses. Of course, the observers in this theory will never use the fact that these are actually these particle models, so we'll do everything phenomenologically. And let's assume this is kind of a different isotope of the same gas. So this is, for example, H, or let's say heavy water. This is a water molecule, or heavy hydrogen, I should say. Let's say it hasn't reacted, but it doesn't. And this would be normal hydrogen. So this has just more neutrons, but it's otherwise identical. So it's a different radioactive isotope of the same chemical material. Now, of course, at that time, this poor guy cannot distinguish them in some way. They're just, they're pretty light. He cannot even weight them. So for them, the two things look just somehow identical. At this time, there was just no way you could distinguish different isotopes of the same chemical material. Now, you may say, okay, this guy is anyway in a bad position because he does something wrong. He doesn't see the difference. But of course, when you think about that, there could be something else we don't know today, which will maybe some property that will be discovered only in 100 years from now. And of course, we don't want that our thermodynamic theory is wrong because we are missing some property a gas has. So clearly, we want that this observer can completely consistently describe this system, but this one should also be consistent in describing the system. Now, what this observer here could do is to say, let's put these things into a common thing with a wall. And now he could remove the wall. And by removing the wall, of course, the things will mix up. Whereas this observer could, of course, do the same thing. So he could put both into the same box with a wall, and he could remove the wall. Now we can ask ourselves, now let's see how these two observers do thermodynamics. Now what do they have to do? They have to define a set of states. Of course, this observer would, of course, consider a different state space. So for him, his state space includes the information whether a certain gas consists of this isotope or of this isotope. So he actually considers this as a two-component gas, and he would say what are the different is the fraction of the different things. So he would, for example, here in this case, maybe say this is a gas with a certain volume and a certain pressure and a certain number of particles of this type and a certain number of particles of the other type, of this point type. Whereas this guy here would say, okay, this is also a gas with a certain volume, a certain pressure, and a certain, maybe number is bad, but he would just know the amount, the number of moles of the gas, but he cannot distinguish the two things. Of course, he should. Now, the state spaces are different. That's fine. That's not very surprising that if you are more detailed, you have different state spaces. But now we come to the operations. So is this now an operation that is adiabatically allowed? So if now this observer defines his framework or his thermodynamics, should he include this process that goes from here to here into his set of allowed adiabatic processes? So he has to define this set A. This is his set A. Maybe I should call it 18 for this observer. So should pi be part of this thing? What do you think? Yes? What do you think? You think it should? Yeah. Okay. So pi should be part of this. Now, what about this observer here? So here we have A of the 20th century. So should pi, is this an allowed process? Who thinks it is? Yes?
Removing the wall should
yes,
be allowed.
Right. Yes, it should be as well. I mean, somehow the intuition, I mean, this is, of course, a matter of definition because people just can define whatever they like, but they want to get something consistent. But the idea is, of course, the adiabatic processes are things we can do without putting the thing into contact with something else. But removing a wall doesn't involve any contact to another reservoir or so on. So both things should be possible. Now, let's consider the opposite thing. So what about this operation? Let's call it pi minus 1. Do you think it should be in this set here?
I think so.
Yes, it should, because from this perspective, this is just including a wall again in the middle, and obviously, I mean, that's unproblematic in some way.
But does that assume that like the pressures and the volume
yes, actually, yes, let's assume that. You're absolutely right. So let's assume here they would have the same P pressure and volume. So I don't want to create a pressure difference or a volume difference or a temperature. So let's even say also the temperature is the same in these cases. Thanks for this remark. But so if this is the case, then yes, he can include the wall again. So what about this guy here? So there seems to be a problem. So obviously he can, I mean, this seems hard to do in some way. So let's, I mean, we can now ask, should he be able to do it? But let's, for the moment, by contradiction, assume that he included it in this set. And then we will see that this will cause a problem to this observer here. Because let's now see what this observer could also do. So this observer could do the following. He could, I mean, let's assume, I mean, now I have to maybe say additional things. So this observer can distinguish the particles. So in particular, should have a mechanism which tells him for each particle whether it's one of this type and one of this type. This is what this modern observer can do. Let's assume that. So what he could also do is kind of to create a kind of demixing process. This is kind of a pretty standard thing considered in thermodynamics. So what he could do is he could take this thing and put a semi-permeable wall into the cylinder, which, so this wall has the property that it blocks particles of the, let's say it blocks particles of the type like that. And then there could be another wall. Maybe I'll put it here. And this blocks the other particles. And now one could do it like that. So one could kind of put the cylinder like this and one like this. And you see that, I mean, the idea, maybe this drawing is a little bit ugly, but here I have, so if I do that, so I start with the two, so these are like two cylinders put into each other. And if I now start pulling them apart, then on this side, because these particles cannot pass, sorry, this has to be, I have to do it the other way around. I did it wrongly. So this has to be the cross, and this has to be that. So these particles cannot pass this wall, so they will not be seen here. So here I have only particles of this type, whereas here I will not have these point-like particles because they are blocked by this wall. And here I still have the mixture. So this is like I have two nested cylinders with these walls, and I pull them apart. So at the end of the day, if I pull them further apart, I will have a situation that looks like that. I mean, probably have seen that in your thermodynamics course, because this is the standard way one actually treats mixtures of gas molecules. So this is not kind of something specific to the Gibbs paradox. So that would be the situation at the end of the day. And now, if you think about what is the energy requirement to do that, then it's actually 0. So you can, the work that is needed to go from here to here is 0, because you see this, for example, this wall is completely transparent to these particles. So this wall will not be hit by any of the two. So essentially it's like, and the other wall will only be hit by that one, but there will be equally many hitting on this thing. So you will see that there is no work requirement. Maybe this is just something you need to, at some point for a minute, think deeply about. And then you see that both walls don't experience any pressure that is not compensated by the other wall of the same box. So therefore, the force you have to apply to pull these apart is 0, ideally, if these walls are made well and so on. Now, but the problem is now, what happens, let's say if I consider this, so if this volume here is volume V, then of course I have at the end 2 volumes V. So I have to compress the whole thing again in order to arrive. So this would be V half. So if I want to arrive back at the situation where I have this, so from here to here, I haven't quite reverted this. I've just come from here to something that looks like this, but has twice as the volume. So I still need to do some compression of the gas to kind of make the volumes again smaller. And now I could calculate how much work this compression requires. And this is a very standard calculation that you have probably done in thermodynamics courses. So the compression step, the work required for that is essentially N times R times T. So this is the gas constant, this is the number of mole I have, and T is the temperature, times log 2, because I make the volume half as large as it was. So this is some calculation you can do with basic laws, assuming it's an ideal gas. So actually, in order to come from this situation to that one would need to execute some work onto the system. But what does that mean? This means, and note that this can be done in a reversible way. So I could also go from here to here. So in other words, what the observer could do, this one here, is he could go from here, also in this direction, but rather than removing the wall, he could do this process in reverse. So he would first let it expand, and then use that to merge the two things. But if he goes from here to here via this process, what happens? He actually gains work. Because if he does this in reverse, he would first let the thing expand here. And when he lets it expand, he gets this amount of work back from the system. So this observer can actually, instead of just removing the wall, he has a more clever process. He has a process from here to here, which with work gain. So there's a process, W, which has a work gain of, I put here a minus, because a gain is a minus, RT log 2. So in other words, he could gain here work. Now, if this process pi minus 1 was allowed, so if he could go from here to here in a simple way, in an adiabatic way, then you could also calculate, because the inner energy is the same, that if he could go from here to here, this process has no work cost. So he would end up in a cyclic process where he would do this transition from here to here via this thing here. So this red arrow essentially means he does this plus this. So this is the way he gains work. So he goes from here to here while gaining work. Then he would adiabatically reinsert the wall in such a way he arrives again here, and then he could do it again, and so on. So this proves essentially that pi minus 1, or this is not the red one, but this proves that pi minus 1 cannot be in his set. Otherwise, he would violate this second law that we saw before. So maybe I should repeat this thing, because this was maybe not completely clear. So what I've done is I constructed, so I said, of course, he can remove the wall. But what I said here is that he can also do something different. He can, to go from here to here, he could first let the thing expand, and then he gains work, and then somehow merge the stuff without any energy consumption. So he can get from here to here and win energy or work. He gets work. But he could go, again, if he now assumed that there is an allowed process from here to here, then this would result in a cyclic process where he would constantly gain work. And this would violate the second law of thermodynamics in the formulation we had. So in other words, we concluded that this is not part of that. But now, you see, the point is now that if we now, so remember the definition, okay, so now we have, I should maybe come to this conclusion at this point. So nevertheless, I should say, if now, so we have now two different descriptions of the system. One is that these are the allowed adiabatic processes, and one is that these are the allowed adiabatic processes. Now I would claim that both descriptions are completely consistent. So they both individually fulfill the first law and the second law. So both descriptions are fine. So this observer will not make a mistake with his description, and this observer will also not make a mistake with this description. The important thing is just we should never mix them. So this observer should not suddenly try to calculate something in this framework, or this should not calculate something in this framework. Yes?
I didn't understand what exactly was the, so what exactly is the reason why this cyclic process doesn't work. So why can't we just remove the wall and then use this mechanism to separate them and gain?
So actually microscopically wide, sorry, I should maybe stress that the process is the one, so you look at this process from here to here, which gains work. So do you agree that there is a process from here to here?
Where I have a semi-permeable membrane, and then I just...
Yes, so you do essentially this in this direction. So you first let it expand so that you get twice the volume, so you have a too large thing. But so first you do that, you have this. But during this process, you already gained work. And now you merge the two gases like that so that you arrive at this situation. And this second step from here to here doesn't require any work. So in total, what you have achieved is you have gone from here to here while gaining work. This is fine. So that's indeed possible. So he can gain work by going from here to here. But if there was now kind of a process, an adiabatic process that would allow him to go from here to here.
So the thing that happens is that you expand the volume of this process on the right, and that's where the work comes in.
Yes, right, yes. So the work comes not from this merging thing, but from the actual expansion of the volume to twice the volume, yes. Yes?
It's not like it's impossible, it's just very unlikely that at the right time, I'm very lucky and very fast.
You say, of course, if there were very few particles, you could indeed go from here to here. So I would say no, but the explanation why we'll see tomorrow. But essentially, the point is that you're absolutely right. If you hit the right time, if you're just very lucky and put the wall inside, then you will get exactly that situation. The problem is that you won't know, because you don't know when is the right time. So even if you did that, it wouldn't be helpful to you. We will see that tomorrow, that even if you achieve such a situation, but you don't have the information that it was like that, it will be essentially useless. Now, in order to convince yourself that you were indeed lucky, you would need to do a measurement. And this measurement will cost you, as we will see tomorrow, as much work as reverting this thing. So you cannot trick thermodynamics, even if you're lucky, in that sense. But that's a very good point. So that will essentially, that refers to the so-called Szilard engine, what you're saying. So what you're saying is exactly the idea of Szilard to drive an engine. And we'll see that this will not work, unfortunately. Otherwise, we will solve all our energy problems very easily. So, okay, but what did we learn now from that? So you remember the definition of I said heat is given by du minus delta W. Now, you see that from the 2015 observer, he can actually gain work from going from here to here. So he could actually make a process which does that thing. And so this means that he would actually extract work from a process which is not possible in this case. So here, there is no way these have just the same thing, the same amount. I mean, he can just remove the wall and reinsert it, but there's no energy involved. Maybe to be more precise, let's do a calculation. So we can actually calculate the entropy difference when we go from here to here. And I didn't now before introduce the entropy. Maybe I should again write it down. So in this framework, I can, of course, introduce entropy like that. And the entropy, what is important is that this definition applies for a reversible process. So that's important. So one looks at, so in order to define the entropy, one has to look at the reversible process. Now, for this observer, the process that goes from here to here is removing the wall and reinserting it is a reversible process. So it's an allowed way of defining the entropy. And because in this process, obviously, there is no heat flow in this frame, according to this framework, the entropy change is 0. So this observer would conclude that the difference in entropy between these two situations is 0. Now, this observer here has a reversible process. I argued that this is a reversible process. I can go in this direction or this, which obviously, or as I described, gives you work when you go from here to here. But because the inner energy, so du of the two situations, so here and here will be the same if you assume that it's an ideal gas. This means that the whole work that I get here will be dissipated as heat. So if this observer analyzes this formula, he has a reversible process with heat here, and so he gets an entropy change. And I don't want to do the calculation now, but if you do the calculation, what you will find is that the difference in entropy is actually exactly N, so the number of mole I have, times the gas constant, times, again, ln2. This is, again, because of I have two components. So in other words, with the same framework, but done filled with different allowed operations, I once come to the conclusion that these systems have different entropies. And if the entropies are different, you see now, of course, that also means that the heat is different. But I now have even a quantitative thing. So I can tell you this entropy is by nRln2 larger than this. So correspondingly, the heat that I would describe as having flown into a system is very different for this observer and for this one. There's a question there, yes?
Yeah, I mean, you said that they are observer for more or less the same experiment. In my view, it's like two different experiments. On the left side, he doesn't know that,
yes.
he has got in both volumes, different kinds of particles.
Yes.
On the right-hand side, he knows that they are different particles.
Yes, so that's absolutely correct. So the way I described how this observer calculates this thing is indeed an experiment that this observer couldn't even describe because he doesn't have the component. However, yes. However, if you're now just asking what is the entropy that the two observers ascribe to this situation and to this situation, then the entropies, I mean, of course, I use the process, which is impossible for this one to define the entropy. However, this situation corresponds to this one and this one to that one. And so I could still ask the question whether they assign the same amount of entropy to the two things. And the fact is that if I have, in reality, this situation here, then this observer, of course, he couldn't distinguish whether it's this one or one with less mixture. But this observer will always assign the same entropy to this thing. So the entropy that, so if in reality I really have this system, this observer would still say, oh, the entropy is actually small, whereas this one would say, oh, the entropy is large.
But the one observer is going from experiment where he has got two volumes of two different kinds of particles, and the other one has got like a mixture. But you don't know that it's a mixture.
Yes, but let's just now ask, what is, I mean, one could now at the end of the day ask the question, what is the amount of entropy you ascribe to that system?
It would be 0.
Yes, here is 0, and here to this system he will ascribe this amount.
Would the observer from 8065 have the experiment of the right hand side, then he would of course got an entropy of the same.
Yes, right. But okay, maybe I should make the point in different. So of course, at the end it depends on the information the observer has. So that's the whole point. So this observer has just less information about the system. He doesn't know that, I mean, if you think microscopically, it's obvious. Microscopically, you would just say he cannot distinguish the particles, so he has kind of a different amount of information than that one who actually can distinguish the particles. But the point is, remember that I drew these particles just as an illustration. So all the entropies were just derived on the possibility or impossibility of operations. So what I'm saying is that if this observer thinks that there is no way of distinguishing the particles, he would arrive at a certain conclusion about the entropy. And this one knows there are actually different particles, he would arrive at a different conclusion. So,
say that the old observer is wrong.
No, that's, yes. So maybe that's good that you say that again, because maybe I should finish very soon. I guess I will finish in a minute or two. Okay. So just to make that point, because that's important. So the statement is not that either of the two are wrong. So the point is both observers, as long as they stay within their framework, will always make correct predictions about everything they can physically do. So this observer will never make a mistake, and this one will not make a mistake either. The point is they just have different descriptions of the system. So because the entropy is not a directly, let's say, operational value. They would just assign a different measure in the same way as for the coin that I had at the beginning. So if I throw a coin, if you say the probability distribution that it's heads is 1/2, and I say no, it's actually 1 because I've seen it's 1, then we are, of course, we make different statements, but we are both right based on the information we have. And this is the same here. So they make different statements about entropy, about heat, but they both make by themselves consistent statements. And all the paradoxes appear if you start to mix these two things. So the Gibbs paradox, which I now didn't state as a paradox, but the Gibbs paradox essentially says there seems to be an inconsistency, but the solution is just we shouldn't mix two things. Either we stay with this description or with this one, and both of them are correct. We're only getting incorrect statements if we mix them. Okay, but I think I will stop here. Of course, we'll continue tomorrow, so we'll have more time to explore that. So tomorrow this was now an introduction into the thermodynamic nature of, the information theoretic nature of thermodynamics, the observer dependence, and tomorrow we'll move into the quantum domain a bit more. So thanks for your attention, and I'm happy to take questions also during the break, or I don't know, now I guess there's not time for questions.
Perhaps in the break.
Yes, I will take questions in the break then. Okay, thanks for your attention.